So I'm just running a little test stream here, because I want to make sure everything is all set in place. Oh, I gotta make sure this is up. And I go here. And then, yeah, and then if I go here. Okay, good. Little bit of delay. Not too bad. And then if I go over here, and I look at my Twitch, mute the tab just to make sure I don't accidentally play anyone else's stream audio. And then I go to my own stream, my streaming. I should be. Oh, okay, wait, that's so peak. How far behind is it? I guess I can check. So if I say test, I gotta see how long it takes to show up here. Oh, not bad. Okay, not a terrible amount of delay. I don't hate that. So what I'm gonna do is I'm gonna put on some copyright-free music, courtesy of Riot Games. And I'm gonna see if the format works. So basically, here's the ordeal. If anyone's actually watching the VOD, or if anyone's actually here, I'm trying to learn methods of theoretical physics within a certain period of time. 48 hours to be specific. So, I guess, without further ado, I'm going to turn up the brightness on my e-ink device a little bit. Or actually, I'll turn on another light in my room. And then, we should be good to start studying. I can actually just reach over here. Pain and agony. Oh. Okay, there we go. And then we don't need the additional light, because I have all the reading light I need. Wonderful. So, I can update the information, because I ended the testing portion. So I can remove the stream test bit. And then start the shot clock. Oh. Okay. And our stream info is updated. Without further ado, shot clock begins now. So first up, we have dimensional analysis. I picked up the Wikipedia article for this. Oh, wow. Thank you, Pandalord. I appreciate that. Yeah, so we're starting with dimensional analysis. The basics of this are, in essence... Okay, good, I have it on pen mode. The basics of this are, in essence, you have some dimension. Say you have length over height, right? If you know these units, right? Let's say it's meters per meter. This is dimensionless. If you know these units, you can get some semblance of information out of things, right? So basically, I'm going to get rid of these. So what I'm going to do is I'm going to go down to the examples on the Wikipedia page, and we're just going to see if we can do them. Shouldn't be too bad. Yeah, see, they give you some basic cases here. So we're going to see if we can use... Also, yeah, Pand, if you're still around, tell me if my audio mixing is good. I should also probably mod you. Can't lie. Because I want to know if the lo-fi is, like, too loud or some shit. So, let's see. Percentages, derivatives, integrals, doesn't matter. We're only looking for our examples. There it is. Simple period of a harmonic oscillator. So, okay. Let's create, if we can, my stuff is bugging. Give me a second. Oh yeah, by the way, I use a Remarkable paper tablet. It's pretty good. Me when I have technical difficulties. Okay. I hate the fact that it's... Okay. That's fine. It's loading everything back up. Reopen, and we're good. We kind of lost time on that, which is tough. But... Okay, share, present, connect to app. And let's accept. There we go. Excellent. Wonderful. Okay. We're good. So what we want to do here is we want to create a note page. And this is basically what we're going to be using for our examples. Hey, it's not supposed to do that. What? That's so weird. Alright, there we go. I'm actually going to adjust my stuff in a bit, maybe. Anyway, yeah. So we've got a simple harmonic oscillator. So like imagine this is a wall and then you have some block. Actually, we're going to say it's hanging from the ceiling because I'm pretty sure that's what they do in the example. So you have some block, which is a simple harmonic oscillator, and it's hanging from the ceiling. Whoa. Cool. So you know that there's got to be some proportionality related to probably this the displacement of the spring from equilibrium, right? There's got to be something related to time. There's got to be something related to gravity and mass. Say this is mass m. They used the spring constant. So I guess instead of saying just this guy, well, no, this is in relation to k. And so basically, if you're looking for maybe like a restoring force, you'll expect units of newtons, right? Which is just units of, let's see. So it's m x double dot, just like meters per second squared. So it's the like kilogram meters per second squared, right? So if you expect something of that form, say we actually don't know you need this displacement, right? Basically, we would say, okay, we have some mg, and then we have some time dependence. This is the acceleration. So this is like a, it's like a constant acceleration. So if you integrate it twice, you'll get x with some time dependence, right? Simple enough. So we have this, and then we have equals k times what? So if we look at the units, this is kilogram meters per second squared. And we're going to assume, what was the units we were given here? Mass per time squared. So kilograms per second squared. So all we're missing here is something with the unit of meters. And the most logical thing it could be is just this displacement that we had right here. Right? Kind of working backwards, but that's really what dimensional analysis is. It's sort of like a physical intuition. So that's good. Actually, it's so abstract that there aren't really any like concrete practice problems for the my God, what is wrong with me today? For the thing. So it just kind of leaves you with whatever you got. So yeah, that's our first example roughly worked through. Here we go. So here we have a more complex example, right? Energy of a vibrating wire. So consider the case of a vibrating wire of length L. So we're going to illustrate this down here. So it's length L with vibrations of amplitude A. And we know it has a density of mass per length, and it's under tension, and we want to know the energy. So, okay. Even just not looking at what we have below, right? Like sort of blanking all of that out. Here's my thoughts. We have some length already, and we have some L squared dependence, right? So if we have the density, which is over L, times the length, which just gives the mass, times the length, or not the length, but the amplitude, times the amplitude, that gives something in the form of ml, and then if we multiply it by, oh, that's a little more difficult. Okay, so it's not quite as easy as it seems. Basically, we want 1m in the amplitude, right? So we have the tension, and we want the units of energy. So maybe the tension times the length, or the amplitude will give us something good. Oh! This is actually closer to what I was thinking over here in this example. Yeah, stuff like this is much weirder for me. Did I really use a pink highlighter instead of yellow? I did. That's crazy. It's kind of dark in my room, I can't lie. Let's see. So if we take L over A, yeah, that is dimensionless. And then E over AS. Is that dimensionless? Yeah, it is. E over AS is dimensionless. The linear density of the wire is not involved is an interesting statement to me. Because in my mind, I would be like, oh, yeah, couldn't you construct something with it that would be, you know, because you could just take it over t squared. But no, I guess you do have to have a physical parameter that has what you're looking for. So because nothing has the this particular parameter. I see. So if I were to solve it myself... Okay. So we have A, S dependence. And then we have... where f is some unknown function. I would hazard a guess that... Yeah, no, that's probably true. I was gonna say, I would hazard a guess that instead you could also have some A of S plus F of L over A, but it is actually much more accurate to say because it's dimensionless, it would be a scaling factor of some sort. So yeah. Okay. That makes sense. I'm going to consider myself having not gotten this one very well, so we'll move on to the next example. Dimensional analysis isn't supposed to take too long. It's not the worst thing in the world. Okay. Rotating disk is an interesting one. So let's highlight our parameters. This time I'll go with orange because it's the most easily visible on my end. So we're going to highlight our thickness. We're going to highlight our radius. Oh, let's make sure we get that. Highlight our density. Highlight our angular velocity. And our stress. And what are we looking for? Demand/capacity. I see. So this isn't exactly something we could fully solve for, because there's nothing we're looking for. However, if I wanted to find, could I have the density be solved in terms of thickness, radius? So if I do density, you could say the units of density are equal to the units of thickness times radius times angular velocity squared. Wait, I'm goofy. I'm lying. What am I doing? It's not this, it's S. And then I add P on the inside. So yeah. I wish there were more good practice problems for this. Honestly, I knew dimensional analysis was going to be a short section. I just didn't think it was going to be this short, you know what I'm saying? So we'll mark this off. So we will say that dimensional analysis... Oh, shit. Where's my shot clock? Dimensional analysis, boom, done. 15 minutes, not bad. Next is a little harder. So next up we have... go to my modern physics folder. We have Laplace's method. So we have two write-ups we can read on Laplace's method, and then a little bit of problems I've done. At the bottom, you can see the main source for these particular problems. This also contains solutions for such problems. So yeah, we're going to be learning how to solve these. Exciting. So first we can begin with our little write-up here. Wikipedia, welcome back. Laplace's method. M is a large number, and the endpoints A and B could be infinite. So, yeah. I don't know if... Let's see. Expanded about x naught by Taylor's theorem. Yeah, so this is the approximation that we're doing. We're trying to find some... basically, we're taking advantage of a Gaussian, right? Because you can say that from negative infinity to infinity, you have some e to the ax plus b squared dx. And this is just equal to the square root of pi over a. Right? Which isn't too bad. So we're going to try to apply Laplace's method. One thing I've always struggled with, though, is changing the bounds on a particular integral. Because, yeah. So... we'll try it. We'll try it. We'll go to our problems and we'll try it. So we'll say we have this, and let's make a new page. So we have our integral from 0 to pi over 2. E to the lambda cosine x. E to the lambda cosine x. Over x squared plus 4. So then we need to transform things to make them a little easier to work with. So we know that e to the ln of n should just be equal to n, right? So e to the negative ln of x squared plus 4 should just equal negative, what the fuck am I on? Should just equal 1 over x squared plus 4. I'm going to very quickly verify that with a calculator of some sort, because I'm like that. So let's just see. E to the ln, or negative ln, x squared plus 4, 1 over x squared plus 4. Excellent, they're the same. Wonderful. Little sanity checks like that are everything. I can't lie. So yeah. That being said, wow, the tracking on this is sublime, by the way. It's very good. Fuck, I love this product. So then we can say that this is in essence equal to 0 to the pi over 2 of e to the lambda cosine x plus, not plus, sorry, times e to the negative ln x squared plus 4. So now we need to find the point we want to expand around. Because we need to find our function of x first. So our function of x should be e to the lambda cosine x minus ln x squared plus 4 and then we can say that we have 0 pi over 2 e to the lambda cosine x minus 1 over lambda. I know, because the limit's approaching infinity. But yeah, ln x squared plus 4. And this gives us our value for m, right? And this gives us our f of x. So we'll do ourselves a favor and take this at the limit as lambda approaches infinity over our current range. So now we have... Wait, hold on. There we go. Yeah, we don't have the boundaries expanded to infinity yet, but when we do, I'm a little concerned about what will happen. We'll find out, we'll find out. So, we have f of x equals... And then we have to find the point to expand it around. Basically, we want f prime of x equals 0. Right? So let's find a good point for that. So we're going to say we take the first derivative, so that's negative sine x minus the derivative of this whole mess. Actually, that should just be easy, because it's just 1 over x squared plus 4 times, what is it, times 2x at the top. Yeah. Equals 0. We can say that the lambda factor over here definitely cancels out this guy. So that goes to 0. So we need to find some point such that negative sine of x is equal to 0. For this, I would suggest... Oh, did my timer stop? Oh no. Wait, that's actually a travesty. That's okay. We'll figure out how much time we lost in just a moment. We lost a couple minutes. It is keeping track inside of OBS. I will note this later. Don't worry. When the stream restarts eventually, we'll start on that time. That's a bit of a disaster, but okay. I understand. I get it. So yeah, that goes to 0. And then we just have sine 0 equals 0. Or really, it's, it doesn't have to be that. It can be sine of pi n, 2 pi n. Checking. Sine. Yeah, it's pi n. So it really works for any of them. this is pi n. However, the easiest point to expand around will be 0. So then if I decide that I want to take my limit as lambda approaches infinity, we need only consider the Taylor expansion of sine x about 0, or cosine x about 0. So we have f of x equals cosine x of 0, so that's 1 plus, maybe plus 1. No, it's minus because we take the derivative. So minus sine x, but we know that that goes to 0 because of how we selected our, so sine of 0 is 0. And then, hold on. Then we have f double prime of 0 over 2 factorial x minus 0 squared. So double prime, that's negative cosine of 0, which is just 1, over 2 factorial, which is just 2, equals negative 1/2 x squared. So 1 minus 1/2 x squared is our function, essentially. So, if we go back to our integral, we have e to the lambda f of x, which is basically just 1 minus 1/2 x squared. And I think it's fine if we integrate over the limit from... Hold on. If I think about this function that we're originally graphing, I want to graph this, but I'm also not sure. Let's check. E to the cosine x over x squared plus 4, and then as this increases and increases and increases and increases, yeah. So we actually only need to graph it from like -2 to 2, to be honest. Because if we go back, yeah, it goes all the way to infinity. Oh, never mind, we get this really neat distribution. So yeah, we are actually going to want to go from -infinity to infinity, probably, to consider all these contributions. I would hope. So let's see. Yeah. Alright, sure. So we'll take it from -infinity to infinity. To infinity. So this is E lambda. And then A would be equal to lambda over 2 for that one, for our Gaussian. So that would be e lambda times the square root of pi over, I guess it's 2 pi over lambda and then as lambda approaches infinity, this guy should approach 0, but my concern is that this actually approaches infinity faster than that approaches 0. So we can check that real quick as well by checking a graph of e to the x over square root of x. And then, yeah, that should approach infinity. Which is rough. I don't like that very much. Unless we're supposed to get an answer in terms of lambda. So let's check using our obsidian vault that we have here for all the sources. We're going to check our work here, chat. Don't worry. Oh my god, did my timer pause it? That's crazy. I think I just have to not minimize it. Yeah, if I minimize it, it just dies. So, we go to the video idea, and then I click on my Laplace method problems. And I go here. Okay. Ah! Similar solution. I did mess something up, though. Okay. I needed a factor of 1/4 in front of my integral for some reason. I think it came from a contributing term. It came from our 1 over x squared plus 4. Ah! Okay, chat. It's because, as x is significantly less, or well, okay, yeah, significantly less than 1 as lambda increases, right? No, hold on. I might be a little goofy. Hold on, chat. This might be weird for me. Basically, this guy right here, it noted that x is on a similar order to 1 over square root lambda, which is significantly less than 1. That's how they did it. So they said we're missing 1/4. So this answer would be correct, except it needs a 1/4 on the outside. And it actually, they went from 0 to infinity instead. I'm not sure why. So it's actually missing a factor of a 16th on the outside. I'm actually going to do this in red ink so that I can't claim I got the right answer later. So we're going to say missed factor (1/16) from 0 to infinity, and 1 over x squared plus 4. Interesting. I don't know how I messed that up. Let's check. Ah, chat. Okay. It's because we're extending our boundaries, right? So we were originally going, imagine for a moment that this is our graph right here. We're originally going from an integral on this guy to I just expanded it in this direction, which adds all this useless bullshit over here. I didn't need to be doing that. So that's where that comes from. That makes sense to me. This still doesn't make sense to me, right? Because if we go back over here, I'm going to do this in blue, right? Just so that future me also knows that this is done retroactively. We have this whole term right here that, like, I don't understand why it's on the order of square root 1 to the lambda. I don't get that. I would imagine it maybe has to do with what we did earlier with this guy. Instead of just arbitrarily saying that it can approach 0, I think instead we're expected to show, hold on, contributes 1/4 y. Again with the timer pausing. I don't know. Oh, okay, good. It jumped. We're good. Less good than I'd like, but we're still there. We're still rolling. No, yeah, that's so strange. So that contribution of 1/4 comes from... Ah! Okay. No, that makes sense. Because if you think about it, right? X is going to infinity, right? So you have 1 over x squared. And then... this guy is approaching infinity. At the bottom. So this is approaching 0. But because of the comparative growth rate between the two, right, you can effectively say, say you have, like, x squared over x squared plus 4 as both of these approach infinity. You actually just have 1/4. That makes sense. I don't know how I was expected to apply that here, because I thought the order of infinity would be different based on what I had found for my representation here. But, you know, I don't know. I didn't think that the natural log of x squared as it approached infinity was on the same order as just infinity. My mistake, I suppose. That's something I need to get better at. Close answer, but not right. Not correct. I'm gonna give this partial credit. We'll say that our final grade, I'll put this in green. Our final grade, I'll give it like let's see, that's 2 small errors. Like a 70%. Not great, not terrible. Alright, so that was problem 1. Problem 2 seems much more on my level. If we just add a note page, we're doing it all again. Oh my god, this is okay. I know nobody's watching, but like this is actually like a really good study vibe because I just get to yap. And if anyone is there watching, like if there are any lurkers, I love you guys. But it's actually nice to be able to talk through my process and not be like super distracted. I should do this while I'm just studying normally. That's a vibe, to be honest. And also my theme is pretty well fit for it. Regardless, I am on the timer. I could use a little mini break. For a little break, I would say let's discuss See, all of these are things that I'm not very good at. But of the one I am good at, it's just because it's just like a basic application of a mathematical concept, right? I was gonna say I could talk about topology maybe, but I was very bad at topology. Group theory, something I really enjoyed. Also something I was pretty bad at. I can't lie. I'm kind of a slacker from time to time. Whatever. Anyway, oh, wait, no. The timer is accurate, because part of my stream was spent setting up the stream and, like, doing an intro. Oh. No, we're so back. We're actually so back. Don't worry about it. I'm surprised we knocked dimensional analysis out so fast. So, okay. Yeah. Just to be fair to us, we're gonna say this is about 0.5 in terms of credit. Even though I rated myself 70%, that's still only worth 0.5. You know what? No. 0.75. 0.75. Why not? Why not? No, we need to be harsh with ourselves. 0.5. 0.5. That's it. Straight up. I wonder if my tablet, while fully lit up, matches the vibrancy of the color on screen. It doesn't. It's so much more muted on screen. I actually like it better on the tablet itself than I do on the stream. That's okay, though. Okay. So, here's what now. Here's what now. For problem 2, right? We're just going to begin. We're just going to start. So we have an integral from 0 to 1. From 0 to 1. And it is of some function e to the negative lambda sine x. This is right up my alley. Because we can now actually just have our f of x be... And I did write things a little incorrectly, because a Gaussian should really honestly be in the form of negative, or like exp, you get it, negative a, x plus b squared. But you get the point. It doesn't matter. No, it does. It matters severely. Don't be like me. But yeah. Okay. So we're going to adjust this a little bit. We're going to say our f of x is equal to sine to the third of x, which means that f prime of x is equal to 3 sine squared x times... Well, actually, hold on. So it's the derivative of the outside times the derivative of the inside, so we're going to go sine x, just for the sake of my own mental. 3 times... What's that going to be? 3 sine x squared times cosine x equals 0. There are 2 such values that we get that we can expand around, which is 0 and pi over 2. But because 0 is already within our integrand range, I'm just going to go with 0. Hopefully that's an okay thing to do. And then the f prime x is equal to 6 sine x times cosine squared x plus, or I guess I should say minus 3 sine x. So we should be able to filter things out a little bit. And we should be able to say six cosine squared x minus sine squared x sine x 1/2, we'll say here. No, this form doesn't sit as well with me as the other one. So we'll just keep the top form. Then we can go and do the following. So our f of 0 equals 0 straight up. Very lucky. F prime of 0 is given to equal 0, which only leaves us with the second derivative here. So this should give us, on the integral from 0 to infinity, f prime prime 0 over 2 times x squared is equal to 0. I believe. If my math is correctly mathing. Because, yeah, you have sine of 0 on both ends. E to the 0. So it's the integral of 1 from 0 to infinity. So we actually... Do we even need to go from 0 to infinity? Because the answer should just be 1. I don't know, maybe I'm crazy here. I don't think we even needed to expand. I think the Taylor series just gave us something nice. And I'm almost 100% sure I'm correct on my derivative. Just to be sure. I will try it. I will try my derivative in a calculator. We like to double check around here. F of x equals... Let me test my results. Sine to the third. Or I guess sine x to the third. To the power of 3. And then f prime of x minus, we're going to say, 3 sine of x squared times cosine of x. Yeah, that's 0. So my second derivative is correct. And then my my third derivative, f prime prime of x minus, should just be 6 sine of x cosine squared of x sine of x to the third. Yeah, that's also just 0. Or at least it should be. Do you drop off? No, you don't. Yeah, that's also just 0. So this is a correct statement for my function. So we're gonna actually just take that. Yeah. So then on the range of 0 to 1, right, we literally just have 1 by our, we don't need to do any fancy expansions. It sends lambda to 0. This is just equal to 1 with no prefactor. Yeah. Huh. Well. Oh. And this should still be running. It is! Yay! Okay. Yeah. Okay. I think I might have fucked something up there. But I'm gonna trust my gut. We're gonna say, I like it. I like it. We're gonna see what the solution manual says, but I like it. Oh. No, I was very wrong. So yeah, they go from 0 to infinity as well. Right? So this is the correct range. So if that's the correct range... Ah! Oh, they use the small angle approximation. Interesting. I don't know if my approach is any less valid. I won't lie, because I honestly want to say my approach is pretty close to valid. However, okay. Yeah. I don't like the way they did that in the book. I can't lie. I mean, I guess technically I'm obligated to mark myself as being incorrect, you know? But that's not okay. So I will put in red. It should actually be the integral of 0 to infinity e to the negative lambda x to the third dx by small angle approximation. It didn't hit me that you would use small angle approximation. Oh, okay. No, that makes sense. Because I guess the idea is you have some Taylor expansion. And then if you have small angle approximation, you just have sine of x is approximately equal to x. Right? This is good, I suppose. I do want to give myself full points here, though. Just on a personal note. Because my math does check out. It just checks out when you do it fully. I'm not sure what additional useful information you get out of doing a small angle approximation. Because the write-up says... you get the majority of your contribution from... I mean, I guess I could always just dust out the integral and see what's up. Fuck it, why not? Alright, so we have e to the negative sine x to the third. And let's just start increasing it. I see! Okay. So I wish I could show you guys this. But basically, if you take the integral, the majority of your contributions are going to come from these little divots, essentially. Like, oh my god. Okay, let me reduce the power on this thing. Let's go to like 4, right? I had to make sure that wasn't Minecraft music, I can't lie. No, but that doesn't make much sense to me. Because I really do feel like the area under it... I don't like that. I can't lie. I'm not a big fan of that. Because here, if I say I have the integral from 0 to 1 of negative this dx, where n is equal to 40, 55. Oh, I see. So, fact of the matter is, as our value for lambda begins to approach infinity, right? As our lambda approaches infinity, the contribution from our integral across the values gets smaller and smaller. I guess I can't really... Here, I guess... 2, 3, 4, 5, 6. Okay. 3. So, let's just assume we're going from, like, let's say a sufficiently large n would be this, right? And then let me visualize this for myself. Yeah, I'd say that's pretty sufficiently large, considering it's a giant black rectangle for me. And then I go up to a sufficiently large 2, 3, 4, 5, 4.1, 2. Okay. That makes sense. So, the majority of the value of this integral... So, this integral is not actually going to evaluate to 1 at all. Right? So, I would actually hazard to say I get a big fat 0 on this integral. Because the very small contributions do actually add up to be a very high number. So, while I have applied the correct ideas and principles, I neglected to note how the graph behaves. Which is a cardinal fucking sin. That's really bad. So, I think we're going to have to end up spending more time on Laplace's method. And I do want to get around to problem 3, but at the same time, I kind of want to take a break and see what will happen if I reset the stream. So for now, I will say, so far, we're an hour into our 48 hours, and our progress is meager. Let's do a little review before we leave things off, shall we? So, what do we know? Where do we fuck up? So, okay. We're doing our Taylor expansion. Okay, that was really sad. I just really relied on autopilot for that one. I forgot this wasn't even, like, necessarily text. Okay. So, we have this guy, right, that we're looking at right here. Right? And we can expand it via Taylor's theorem, which we did. And we approximated it like this. However, did we miss something? Because I think... I think we have definitely missed the way we need to select our approximation. Because Taylor's makes sense. However, in the case of the... Oh! Yeah, no. We should have done small angle. I really do feel a little goofy for forgetting that. So we have this method. We honestly don't need the proof. The formal statement is good. And the fact that it's, like, supposed to be just this, right? Like, this is the core idea, right? And we're still fucking it up. That's not good. We need to be on top of selecting our criteria for, like, approximations and such. So, yeah. Give me a little time to, like, nap on this. I can't lie. Give me a little time to sleep on this one, chat. Because it should, keyword is should, be relatively easy. But it's not. Because then if we go here, too, like, we have our next one that we're going to have to do a conversion from log to... I don't remember how to do that off the top of my head, either. That's probably something I should learn. I think it's just, like, what? Like... log of that over log of e to get it in terms of the power of e. Because to get something in terms of log 2... Oh shit, it's still red. Because to get something in terms of log 2, right, you basically have log 2 equals log of 10 over log of 2. So instead of that, I'm just gonna put log of e on the inside here, and we call that a day. We'll get that sorted out. So yeah, problem 3, we will just do the basic Taylor's approximation, and we are actually gonna shape out this graph. And yeah, hopefully we can get with our partial credit, we can get 3, 4, and 5. If not, we're actually going to take the L on Laplace's method for the sake of our 48-hour challenge, which would be really bad. We'd honestly need a run back. I'd need to find more problems later. Yeah. Honestly, though, plenty of time to learn things. Yeah. If you did stop by the test stream, thank you. I really appreciate that. Yeah, I'm going to real quick. Where's my mouse? Oh, now you see me, now you don't. I'm going to real quick pause our timer here. Pause the shot clock. So, excellent. Now I have that time noted, and I have our best time for dimensional analysis noted too. And I'm just gonna let my my tablet recharge a bit. Boom. Oh shit. Boom. There we go. Yeah. If you stop by, again, I want to say a resounding thank you. I know this is probably a very niche stream that not many people will enjoy. But if you are enjoying, I appreciate you. Thank you so much for being here. Yeah. And let me just do a little bit of entry on those splits. So for now, it's just me and me in the chat in the dark. So we are gonna save our best times. And I have neglected, like a fool, to save, my time. But it should still exist in the VOD form. So yeah. Let's edit our splits. Okay. Good. Alright. Thanks for stopping by. I will see you all later. Ciao.